Hello, this is Eric from UNC Charlotte. Today, we will see how the network topology of distributed memory machines impacts the practical performances that one experiences. Distributed memory machines are composed of nodes with independent memory. Applications running on such machines need to communicate through the network to coordinate the execution of the application. The mental model of the network that one should typically think of is that of a clique. In a clique of P processors, each processor is connected with every other processor with a dedicated communication link. Cliques are a very good network topology because all the communications are completely independent. So you can build your application without having to think about network topology or network interference. But cliques are impractical. One would need roughly p²/2 links to build such a network. If you want to build a machine with 100 nodes, you would need 5,000 network cables. Quickly, cliques do not scale to build realistic machines. So machines are not built using clique topologies, but the properties of a clique are still desirable. And machines are built to provide performance close to that of a clique. One of the earliest topology of networks are chain networks. Each node is connected to two other nodes, except the extremities. This is a practical network topology that we used to build. Can you think of why we do not build networks like this anymore? Pause the video to think about it. There are two main reasons. First of all, networks like this are very brittle. If a single machine breaks, the networks become disconnected. Also, the performance of such a network is very poor. Sending a message from machine 0 to machine p-1 requires to traverse every link in the network. The maximum latency of communications over such a network would be in theta of p. A hypercube is the theoretical construction for networks. A hypercube of dimension n is built by taking two hypercubes of dimension n-1 and connecting the sister nodes together. They use logarithmic degrees to guarantee high bandwidth and low latency. However, constructing the machine has proved to be difficult past 1,000 nodes. Building your network as a tree is also something that has been considered. Here we show a binary tree, but any hierarchical structure works similarly. Hierarchical networks are easy to construct in practice, as each node only requires a few connections. Here, up to 3 per node. The latencies in the network are also very good. The height of the tree is in log p, so the longest distance in the network is 2 log p. Though hierarchical networks are still very brittle, any link going down would disconnect the network. Also, while the latencies are pretty good, the only communication path from anywhere from the left of the tree to anywhere on the right of the tree will have to go through node 0. It means that the links that are higher in the tree are going to receive more traffic, and so they are going to be more congested. We don't build hierarchical networks exactly like that, but data centers are often built on the same principles, using a fat tree topology. They often make the links higher in the tree have a higher bandwidth, and they often have redundant links to help with reliability issues. Organizing nodes on a grid has good properties. Each node has few connections, making the machine easy to build in practice. The network also has a decent latency. If the grid is square, communicating from one corner to the other one is the longest communication, and this would require going through 2 √p links. The network is also fairly robust. One would need to remove √p links to disconnect any significant part of the network. The existence of many paths between any 2 pairs of nodes is also very good for bandwidth. In practice, we do not build networks as perfect grids. We loop them around and form a torus. A donut is a 2-dimensional torus. Recent machines were built using torus networks. In particular, Sequoia was a machine built by IBM at LLNL using a 5D torus network. It was the fastest computer on the planet in June 2012. and Fugaku in Japan currently uses a 6D network, and it is the fastest machine on the planet at the moment. Some large modern supercomputers are being built using Dragonfly networks. Machines in the same rack are completely connected. Then, each machine is also connected to a fixed number of machines in other racks following a regular pattern. Analyzing and programming such network is particularly difficult. The patterns are carefully selected to ensure a logarithmic diameter and a high bandwidth between any two sets of nodes. Network topology will greatly impact the performance of a distributed memory machine. Machines are built to be practical to construct and operate, while providing low latency and high bandwidth between any two nodes. They are usually built in a structured way to enable communication algorithms to be graceful. While network topology matters, critical operations are usually implemented inside of a programming middleware, and that middleware accounts for network topology. So when programming a machine, we do not often need to worry too much about its actual topology, and we often program the machine as if it was a click.